Hello, and welcome to Lecture 4 of Parallel Computing. So today we'll be looking at different ways to analyze the performance of a parallel program. So when we talk about performance, we're usually talking about the speed of the program. So if you take a program and you run it on one processor, and then you compare that time to running the same program but using K processors, right? Then ideally, you want the program to run K times faster. Okay, so if we look at this picture, right, then different things can happen as you change the number of processors you're using to run the program. Okay, so we could have the program runs, so if we're using K processors, right, we could have that the program runs K times faster, right? We could have that the program runs somewhat faster, but less than K times faster. Okay, so this is called sublinear speedup, right? And sometimes you can even have a situation where the program using K processors, it runs more than K times faster. Okay, so this is called superlinear speedup. Okay, now in practice, usually we do not get superlinear speedup or even linear speedup. Usually we get sublinear speedup. Okay, so in fact, if we look at the second plot below this, right? So this is showing some actual data from running some application on Amazon Cloud Computing. Okay, so now here the x-axis is showing how many different processors we're using, or how many different nodes we're using, right? So this is the amount of parallelism that we're using. Okay, and then the y-axis is showing the amount of speedup that we're getting. Okay, and this dotted line over here represents exactly linear speedup. Okay, so now you see that initially as you increase the number of processors, we do indeed get superlinear speedup. Okay, so this is true until we hit about 40 processors. Okay, but once we hit, or rather 40 nodes. Okay, but once we hit 40 nodes, then as we add more nodes, we're not getting any better performance. Okay, in fact, once you go past something like 50 nodes, right, if you look at the performance, it is actually decreasing as you add more processors. Okay, so the program is actually slowing down as you add more processors once you go past 50 nodes. Okay, so basically today we want to understand this type of behavior, right? How do we characterize the amount of speedup that a program is getting, and how do we understand the reasons for the speedup? Okay, so to do this, we want to identify things like performance bottlenecks, right, which impede our speedup. Okay, and then we also want to compare different algorithms that solve the same problem, and we want to compare them in terms of their efficiency and the speed up that we get from them. Okay, now for this analysis, we'll try to be as abstract as possible, because if we try to take into account too many details about the hardware architecture, for example, right, then we have an analysis which is only specific to a particular type of hardware. Right, so it doesn't generalize to parallel computing in general. Okay, okay. So we'll try to make our models capture essential properties about the behavior of the program, but nevertheless, we'll try to ignore as many details as possible to generalize our analysis. Okay, and in addition to this, we're going to be using asymptotic analysis, meaning that we consider the behavior of the program as we increase the problem size. Okay, so we don't look at very small problem sizes because in those regions, certain behaviors that are non-general could be occurring, right? Certain sort of bizarre behaviors could be occurring, right? So we want to look at more general behaviors, and so we'll look at the problem as we increase the problem size to very large sizes. Okay, so let's first define some terminology. Okay, so we're trying to measure the amount of speed up that a program is getting as you increase the number of processors. So let's fix a problem X. Okay, and let's say that we have a parallel algorithm A which can solve X. Okay, now we're going to define T sub S to be the minimum amount of time to solve X using one processor. Okay, so this is basically the time for the best sequential algorithm for solving x. Okay, the best possible, the smallest possible time for solving x on one processor. Okay, now T1 is going to be the amount of time that algorithm A takes to solve x using one processor. Okay, so now A is a parallel algorithm, so we can use different numbers of processors. Okay, now if we use just one processor for A, right, then we're basically looking at the sequential running time of A. Okay, now we know that T1 is going to be at least as large as TS, right, because TS is the fastest possible time to solve the problem sequentially, right, and then T1 is the sequential time that algorithm A takes. So T1 is going to be at least as large as TS. Okay, next we're going to define TP. Okay, so this is the amount of time that algorithm A takes to solve x using P processors. Okay, so this is like the parallel running time of A when we're using P processors. Okay, so next we'll define several ways of measuring speed up. Yeah, so the first measure for speed up is called absolute speed up. Okay, we're going to write this S star sub P. And so this is going to be defined as TS divided by TP. Okay, so what this is capturing is that TS is the time for the best sequential algorithm. Okay, and TP is the time for algorithm A using P processors. So we're basically comparing algorithm A, right, with the best sequential algorithm when we have P processors for A. Now, the problem with this absolute speedup is that we usually don't know what TS is, right? So for many problems, we don't know what the best sequential algorithm is. Okay, so instead, we can use another measure called relative speedup. Okay, and this is also called scalability. So this is denoted as S sub P, and this is defined as the as T1 divided by TP. Okay, so this means that we're comparing the time to solve x using one processor for algorithm A versus when you have P processors. Okay, so in general, this SP is going to be a number that's larger than 1, right? Because T1, when you only have one processor, right, it's going to take you a long time to solve this problem, presumably, right? Whereas if you have P processors, it takes you less time. Okay, so T1 is going to be larger than TP in general. Okay, and so so the reason we call this relative speedup is that we're comparing A with itself. Okay, but we're varying the number of processors that we're using. Okay, now we're mostly going to be focusing on scalability, or this relative speedup, in this lecture. Okay, because again, we don't really know what TS is, so it's hard to compute what the absolute speedup is. Okay, next we have something called work. Okay, so work is going to be equal to the number of processors you're using times the amount of time that those processors run for. Okay, so this is basically the sort of the total amount of computation that was consumed by these P processors. Okay, because we have P processors, they each run for T sub P amount of time. So the total amount of computation that they did, right, in this TP amount of time is equal to the work. Now, we have this property that P times TP, right, or the amount of work, is going to be at least T sub S. Okay, and this is because T sub S is the amount of work that the best possible algorithm does to solve this problem, right? I mean, it's a running time of the best sequential algorithm, right? But because the sequential algorithm is using just one processor, then the running time of that algorithm is equal to the amount of work that it's doing. Okay, now W sub P is the amount of work that our parallel algorithm A is doing. Okay, and so this the amount of work that A does has to be at least as large as the amount of work that the best possible algorithm does. Okay, so we have WP larger than at least equal to T sub S. Okay, and lastly, we have this lastly, we have this expression for efficiency. Okay, so efficiency is going to be defined as the speed up divided by p. Okay, and yeah, and so usually this is going to be a number less than 1. Okay, so so if we go back to the plot on the previous page, right? If we're in the linear regime, right, then in that case the efficiency is going to be exactly equal to 1. Okay, because the amount of speed up that you get is exactly equal to the number of processors you're using. Okay, if you're in the sublinear regime, right? So if you're down here, right, then the speed up you're getting is going to be less than the number of processors you're using. So that's going to be a term less than 1. And if you're in the superlinear region, right, then your speed up is then your efficiency. Okay, so when you have linear speed up, you have exactly efficiency equal to 1. For linear sublinear speed up, you have efficiency less than 1, and for superlinear speed up, you have efficiency larger than 1. Okay. Yeah, so usually we have efficiency less than 1, and this is because whenever you parallelize, right, if you have multiple processors, you're going to pay some overhead for having all of those processors. Okay, so we'll see more about that overhead later. But because of this overhead, you're not going to get exactly perfect speed up. You won't get linear speed up. You get sublinear speed up. Okay, but as we saw with the Amazon example, right, it is possible in some cases to get superlinear speed up. Okay, so in fact, you can think about what are the reasons that you can be getting linear speed up, right? So that's quite an interesting exercise. Okay, so let's talk about these overheads. So linear scalability basically means that the speed up that you're getting is exactly proportional to the number of processors that you're using. Okay, and as I said, this is hard to achieve because of speed up, because of overheads. Okay, so what are these overheads? Well, if we're using multiple processors, then of course the processors need to communicate with each other, right? And they also need to synchronize with each other. Okay, so all of that incurs a cost. So we talked about communication cost last time. We saw that this is actually quite a substantial cost in terms of the overall running time. Okay, another source of overhead is that when you parallelize, right, ideally you want to have all the processors be working all the time. Okay, but that's usually not possible to achieve. So when you take this large problem and you break it up into multiple small pieces, right, sometimes some pieces are larger than other pieces. And so the processors which are solving those larger pieces are going to take more time than the ones solving the smaller pieces. Okay, so basically you have a load imbalance between the processors. Okay, and when that happens, you're going to have some processors, they're going to finish their small pieces very quickly, and then they won't have anything to do. Okay, so that's another type of overhead. Okay, and then another source of overhead is that when you do a parallel computation, right, sometimes you're going to find that so the processes need to communicate, but sometimes you find that this communication cost is so high that instead of having one process, let's say, compute something and then communicate that result to another process, right, you would rather have the other process just redo the computation. Okay, so sometimes it's actually faster for you to redo the computation. So for example, if you have two processes and the first one does a very simple computation, right? Let's say it adds two numbers, okay? So that's a very fast computation, right? Now, if the second process needs to know that sum, right, then you have two choices. Either you can have the first process do the sum and then transfer that sum, communicate it to the second process, right? Or you could just have the second process compute the sum by itself. Okay, and because it's such a simple thing that you're doing, just computing a sum, right, it's probably cheaper for the second process just to redo that computation. Okay, but if you redo computation in this way, then you're actually increasing the total amount of work that you're doing, right? Because previously you were doing one addition, and now you're doing two additions. Okay, so you increase the overall amount of work that you're doing, and that's another source of overhead. Okay, another source of overhead is that, so we wanted to compare with the best sequential algorithm, right? But sometimes the best sequential algorithm is actually not parallelizable. Okay, so if that's the case, then instead of trying to take the best sequential algorithm, but you're not able to parallelize that, in order to reduce the running time, you would rather take a suboptimal algorithm, right, which does more work than the best sequential algorithm. However, the suboptimal algorithm might be more parallelizable than the sequential algorithm. Okay, so a good example of this would be something like if suppose you're trying to compute shortest paths. Okay, well, there are different algorithms. The most efficient sequential algorithm that we have currently is Dijkstra's algorithm. Okay, so Dijkstra's algorithm basically does linear work, right? So Dijkstra's algorithm, we can actually sort of write out the amount of work, right? It does basically order m plus n log n amount of work, okay, where m is the number of edges in the graph and n is the number of nodes. Okay, however, this algorithm is not parallelizable. Okay, or we don't have very good ways of parallelizing Dijkstra's algorithm. Okay, now alternatively, you can take some other algorithm for solving shortest paths, for example, the Bellman-Ford algorithm. Okay, now this algorithm is actually much less efficient in the sequential setting, okay, because it does like order m times n amount of work. Okay, so it's much slower than Dijkstra's in the sequential setting. However, this algorithm is highly parallelizable. Okay, it's actually very easy to parallelize Bellman-Ford. Okay, so depending on the situation that you're in, you might actually choose to run Bellman-Ford in a parallel setting instead of Dijkstra's. Okay, even though Bellman-Ford does more work overall. Okay, so that's another source of overhead. Okay, so now we're going to talk about several different models or several different ways of measuring the performance of a parallel program. Okay, and the reason we have several different ways of measuring this performance is because none of these models, none of these performance analysis models perfectly captures parallel performance. Okay, they all make some assumptions about the program. Okay, so they're all suited. They're all best suited towards certain situations, right? So and there's no one general model that covers all situations. So depending on the actual program that you're trying to analyze, you might want to use different ones of the models that we'll talk about. Okay, so now I'm going to present the first model for the analysis, which is the DAG model. Okay, so the DAG model basically tries to look at a computation as a graph. Okay, so in fact, it's a directed acyclic graph. That's why it's called the DAG model. Okay, so what we're going to do is we're going to look at all the computation and the communication in this that we're doing in this program, and to represent this as a graph, we're going to create a bunch of nodes. Okay, so each node is going to represent one part of the overall computation that we're doing. Okay, furthermore, we're going to make edges between the nodes, directed edges. And the directed edge basically means that, for example, if one node points to another, right, like here 1 points to 2, right, then this means that you have to do the task associated with 1 before you do the task associated with 2. Okay, so so these edges are giving the precedence relation between these tasks. Okay, so again, we take a big computation, right, and then we break it up into a bunch of small small tasks. Right, and then we put in edges to represent the precedence relation between the tasks. Okay, yeah, so this is saying what I'm saying. Oh, and then furthermore, we can have weights on these nodes, and we also can have weights on the edges. Okay, and so so the weights basically represent the size of each task, or maybe the size of a communication Okay, so so if we put a weight of, let's say, 5, right? So this might mean that you have to do sort of 5 units of computation, right? And here you could have a weight of 2, right? So here task 2 is somehow smaller than task 1, right? So and then we can also have weights on the edges. So for example, if after you do task 1, you need to communicate some data to task 2, right? So in that case, there's a precedence relation between 1 and 2. Right? And furthermore, to do that communication, you might have to incur some sort of cost. So maybe you put a cost of, let's say, 3 on here because that's the cost. Okay. All right. So So that's the model. Some other things are, because this is a DAG model, right? So it's a directed acyclic graph, okay? So we don't want to have cycles, okay? So, so this basically means that the computation has to finish eventually, right? Because you can go from like sort of the top node, which doesn't have any incoming edges, right? And then if you keep following these outgoing edges, eventually you get to another node, which also doesn't have any outgoing edges. Okay, so that's sort of like the end of your computation. Okay, now we want to define something called the critical path in this DAG. Okay, so the critical path is basically the longest path in this graph. So if we do an example over here, so let's say that we take this this red DAG over here, right? And suppose that all of the nodes have the same size. Okay, so suppose they all have size 1. Okay, for simplicity, and suppose that all of these edges, let's say they have a cost of 0. Okay, so in that case, the critical path is simply the longest directed path in this graph. Okay, so that would be something like maybe this one. Right, I'm not really sure, but I think that looks like the longest path, and so that would be the critical path. Okay, and so the reason we're interested in the critical path is because basically, as we'll see on the next slide, a computation has to take at least as much time as the length of the critical path, no matter how many parallel processors you use. Okay, right, no matter and so the reason for that is that, maybe I should just keep this, right? So, so if you look at this critical path, right, you have to do all of these tasks in sequence, right? Because of these precedence relations between these tasks. Okay, you have to do 1 before you do 3, before you do 5, and so on. Okay, so no matter how many processors you have to finish 1 before you start 3, and you have to finish 3 before you start 5, and so on. Okay. So no matter how many processors you have, the amount of time they have to run for is going to be at least equal to the length of this critical path. Okay, yeah. So what's this? All right. So for some reason I can't erase this. Okay. So now let's maybe look some more at this DAG. Let's see. Yeah, I guess I'll do this on this slide. Okay. So here what we have is a computation. Well, we actually have 3 computations. Okay, the red, green, and blue computations, and we've broken each of them into a DAG. Okay, and then on the bottom over here, right? Here we're looking at how would you actually execute these DAGs on a parallel computer. Okay, so in this setting, we have 4 processors, okay, CPUs 1 through 4. And what we're doing is we're assigning these tasks, okay, these red, green, and blue tasks to these processors. Okay, so for example, initially you assign, now when you do these DAGs, right, you have to start with a node that doesn't have any incoming edges, right? So we have to start with the red, green, and blue nodes number 1, okay? So first of all, we're gonna assign those to our processors. Okay, so you basically give T1, the red T1, to CPU 3, the blue T1 to CPU 2, and so on. Okay, and this T1 has some size. Okay, so the size of T1, the red T1, or sorry, let's go for the green one because it's easier to see. Okay, so for the green T1, right, it's got some size like this, right, and so it needs to run for a certain amount of time on CPU 2. And then once you're done with the green T1, then now you can run the green node 2. Okay, so now you can, so after you're done with the green 1, you can run the green 2. Okay, and then after you're done with the green 2, right, then you actually have 2 tasks available to you. Okay, you can either run 3 or you can run the green 4. Okay, now in this case, right, for this example, we're choosing to run T4 first. Right, you don't have to run T4 first, right, and then actually we're going to assign T3 to a different processor, right? And we can do this because there's no precedence relation between 3 and 4. So therefore, you can run 3 and 4 concurrently, okay? Right? If there were an arrow, let's say between 3 to 4, right, then you would have to do 3 first before you do 4. But because there's no arrow, we can actually do both of these concurrently. Okay. Now, in this example, they're not doing 3 and 4 concurrently, but you actually could, for example, you could do T3 and T4 at the same time. So, for example, you could switch maybe the order of this blue node, right, and the green node. Okay, so that way you would be doing the green 4 and green 3 at the same time. Okay, so so basically, the way that we can schedule these DAGs onto an actual CPU, okay, is that we take these nodes, right, and then we have to, whenever you want to process a node, you have to make sure that all of the ancestors of that node have already been processed, right? So all of the preceding tasks are done. But if that happens, then you can take a node and then you can assign it to any CPU which is free. Okay? Yeah, and so this is how you go from these 3 DAGs to this actual schedule that is shown below. Okay, and then the total amount of running time for this program, okay, is basically the time when all of these processes have finished. Okay, so so this takes about 140 steps. Okay. All right, so something else that you can see is that here you have a lot of white regions, okay? And these are indicating times when a processor is not doing anything, okay? So this is, in fact, some of this overhead I talked about. And this is coming about because of load imbalance, right? So you see that, CPUs 1, 2, and 3 are doing a lot more work than CPU 4, right? CPU 4 is idle for a lot of the time. Okay, so all right. So now let's look at how we can use this DAG model to say something about the speedups that we can try to get. Okay, so yeah, so we need to define some more values. So first, let's let C be the sum of all of the node and edge weights in G. Okay, so remember that we said the nodes and the edges could have weights on them. C is just going to be the sum of everything. Okay, now C basically represents the total amount of work that you need to do for the DAG, right? Because the work is either going to be computation, right? So that would be the weights for the nodes, right? Or it's going to be communication, and that's going to be the weights on the edges, okay? And if you sum all of that, right, then you get the total amount of work that you're doing for the computation. Okay, now D is going to be the length of this critical path that we talked about, okay? So for example, D is going to be this, the length of this, okay? It's going to be the sum of the weights of all of the nodes and edges on this path, okay? We're going to pick the path where this the sum is the largest, right? And that's going to be our critical path. Okay, so then TP is going to be like before. It's going to be the time taken by P processors to execute this entire problem, to solve this entire problem. Okay, so that's the parallel running time. Okay, and then T infinity is going to be the minimum amount of time it takes to execute G using an arbitrary number of processors. Okay, so let's say that you have an infinite number of processors. Okay, how fast can you solve this problem? Okay, TP is when you have P processors. T infinity is when you have as many processors as you want. Okay, so we're going to assume that when you have P processors, each processor can do 1 unit of work per time step. Okay. Now, if you have processors with different speeds, then you can just sort of renormalize all those processors, and this analysis would still work. Okay, now we can say 2 things about how much time these parallel processors are going to take. Okay, so the first thing we can say, and this is called the work law. Okay, so this is saying that P times TP is going to be at least C. Okay, so what this means is that, now remember that P times TP is the amount of work that these processors are doing in this computation, right? So the processors are going to take TP amount of time to solve the problem, right? And then since you have P processors and they each do 1 unit of work per time step, then P times TP is the total amount of time. It's a total amount of work that they've done by time TP. Okay, and this has to be at least as large as C, because C is the total amount of work that exists in the problem, right? So if you want to solve the problem, you have to at least do all the work in the problem, right? And the amount of work that you're doing in TP time is just P times TP. And so this has to be at least as large as C. Right? So now this could actually be P times TP can be larger than C. Okay, when you have overhead, when you have, for example, idle time. Okay, this P times TP can be larger than the minimum amount of work. Okay, but it's got to be at least as large. Okay, so because of the work law, then if you just divide both sides by P, you get that the parallel running time has to be at least equal to the size of this task, okay, to C divided by the number of processors. Okay, so now this is a lower bound on the parallel running time. Okay, it's saying that no matter what algorithm you use, okay, as long as you're using just P processors, then your running time is going to be at least C divided by P. Okay, so next we have this span law. Okay, so this one is saying that this T infinity is going to be at least as large as D. And so what this means is that no matter what algorithm you use, and no matter how many processors you have, you could have an infinite number of processors. Okay, your running time is going to be at least as large as the length of your critical path. Okay, and the reason for this is just what I said previously, which is that because this is a critical path and all of the nodes are dependent on the preceding nodes in this critical path, right? Then no matter how you assign your processors, right, you have to do the nodes on this critical path in order. Okay, one after another. You have to wait for the previous ones to finish before you can start the next one. Okay, so the time that you need to solve the tasks on this critical path is going to be D, no matter how many processors you have. Okay, so therefore we have the span law. Okay, so that's basically the DAG model. Okay, it's to take a computation and then form a DAG out of it, right? And then once you have this, then you get these two lower bounds. The work law, right, which says that your parallel running time has to be at least C divided by P. And then the span law, which says that your parallel running time has to be at least as large as D. Okay, because of course we have that T of P, right, is going to be at least as large as T of infinity, which is going to be at least as large as D. Okay, so we get these two useful lower bounds, two lower bounds, and it turns out that oftentimes they're quite useful for sort of evaluating the performance of our algorithm. Okay, so next I'm going to move on to a different way of measuring performance, and this is called Amdahl's law. So this Amdahl's law gives you an upper bound on the maximum speedup that your program can achieve. Okay, and the way it works is that suppose you let T1 be the running time of the program. So you have some parallel program for solving some problem, okay? And you let T1 be the time to run the program when you just have one processor. Now, also, we're going to assume that part of this program is inherently sequential, okay? So no matter what you do, you cannot parallelize a part of this program. Okay, so so there are some things which are sequential, right? So for example, this Dijkstra's algorithm. Okay, so this is hard to parallelize, and there's some things that you just have to do sequentially. Okay, so we assume that you have f fraction of this program that you have to do sequentially. Okay, so so since T1 is your overall running time, and you have f fraction which is sequential, then the total amount of work which is sequential is going to be f times T1. Okay, and the remaining work in the program, right, everything that's not sequential, we're going to assume is perfectly parallelizable. Okay, so the remaining work is going to be 1 minus a fraction, the sequential fraction, times T1. We're going to assume that work is completely parallelizable. Okay, so now let's look at the running time. So T1 is the running time on using one processor. Okay, now assume you have P processors. What is the running time? So when you have P processors, the sequential part, okay, it doesn't care how many processors you have. You have to do that sequentially. So the running part for the sequential time is going to be the same both in the sequential version and the parallel version. It's going to be f times T1. Okay, the parallel part, okay, this can be parallelized, okay? So here you have 1 minus f times t1 amount of work, and when you have p processors, right, it's going to go p times faster. Because here, for Amdahl's law, we're going to assume that you have a perfect linear speedup for the parallel part, okay? And you have no speedup for the sequential part. Okay, so then the total running time for p processors, right, it's just the sum of the sequential part and the parallel part, okay? So it's going to be f times t1 for the sequential part plus 1 minus f times t1 divided by p for the parallel part. And this is our parallel running time, TP. Okay, so now let's look at the, so this picture actually gives you another way to look at this, this Amdahl's law, okay? So what it's saying is that, when you run this program on one processor, you have a sequential part and a parallelizable part. And when you switch to multiple processors, right, the sequential part takes the same amount of time as before. Right, because it's sequential, okay? But the parallelizable part, if you have many processors, right, then you can divide this among your processors, right? And then you can run all of these parts in parallel, and here you do get a speed up. And then the total running time in the parallel setting would be the sum of these two parts. Okay, so that's like sort of a proof of Amdahl's law. Now once we know the parallel running time t sub p, right? Now we can look at the speed up that we get. So the relative speed up. Okay, so this is computed by comparing t sub p with t sub 1. Okay, so you do t sub 1 divided by, so here you have the expression for t sub p, and then if you simplify, if you divide out by t1, you get that your speed up is basically equal to this expression. Okay, 1 divided by f plus something. Okay, so now let's look at the speed up expression. Okay, so what you see is that if you increase p, okay, then this term here is going to get smaller. Right. However, no matter how small it gets, right, this term here, this f term, okay, this is not changing. Okay, so therefore your speed up here is always going to be at least, it's going to be less than 1 divided by f, right? Because this term here, right, is always going to be non-negative. Okay, so no matter how many processors you're using, this speed up is going to be less than 1 divided by f. Okay, so this is an upper bound on the speed up that you get, no matter how many processors you use. Okay, now let's take this expression from Amdahl's law for the speed up, and let's look at what happens when we use some actual numbers for the for f. Okay, so this expression is in terms of this sequential fraction, this f over here, right? So let's try some actual values for f and see how much speed up we're going to get. Okay, so in this plot, right, on the x-axis we have different numbers of processors. Okay, so this is actually increasing exponentially from 1 to 2 to 4 and so on, going up to like 65,000 processors. And then on the y-axis, we're looking at the speed up that you get using that number of processors. And so we have these different lines here, and they represent different values for f. Okay, so for example, this blue line over here, right? So this is saying that the sequential portion of your program is going to be half of your program. Okay, so half of your program cannot be parallelized, and the other half can be parallelized. Okay, the red line is saying that 75% of your program can be parallelized. Okay, so there's 25% that's sequential, right? And then here there's 10% that's sequential, and then here there's 5% that's sequential. Okay. Now what you see is that basically remember that Amdahl's law says that S of P, right, the speed up you get with P processors, no matter how many processors you have, is going to be at least as large as F, 1 divided by F. Okay, so therefore for this 50% thing over here, right, we have F equals 1/2, and so this, this is less than or equal to. Okay, so we have that for this 50% sequential part over here, your speed up is never going to be more than 2. Okay, so here you see that no matter how many processors you use, right? You could use 60,000 processors, but your speed up is not more than 2. Okay, for the red line, right? We have that the sequential part is going to be 1/4, and so your speed up is never more than 4. Okay, it's always going to be less than 4. And then even for this green line, right? So here you have 90%, 95% of your program is parallelizable, right? There's only 5% that's sequential, right? And yet you see that we can never get more than 20x speed up, right? And then, even if you use, let's say 1,000 processors over here, okay, you're getting something like 19 times speed up. Okay, so you have 1,000 processors, but you get less than 20x speed up. Yeah, so basically, if you just look at these plots over here, you become very pessimistic, and you start to think that in fact, there's no point building these large parallel computers, right? Because even if I have thousands and thousands of processors, right? If I have a program which is quite parallelizable, right? Let's say it's 95% parallelizable, okay? But then even if I use thousands of processors, I won't get more than 20x speed up, okay? So why should I bother building these large computers? Okay, but this is somehow not quite correct, right? Because we know that it does make sense to build these large computers, because in practice we actually get very large speedups on problems. Okay, so why is it that Amdahl's law predicts that we cannot get large speedups, and yet in practice we do observe large speedups? Okay, so this indicates that there's something incomplete or something not quite right about Amdahl's law. Okay, so next we're going to look at another law, right? So this is another way of looking at parallel performance, and this is somehow probably closer to reality than Amdahl's law. Okay, so this is called Gustafson's law. So this basically tries to explain why real parallel systems usually get good speedups, right? So we can get 1,000x speedups, 10,000x speedups. Okay, unlike what Amdahl's law predicts. Okay, so the reason Gustafson's law is different from Amdahl's law is that it makes the different assumption. Okay, Amdahl's law assumes that we have a fixed problem size. Okay, so we have a fixed problem consisting of a sequential part and a parallel part. And then the only thing that you vary is the number of processors that you use, right? So you fix the problem, but then you increase the number of processors, and then you look at your speed up. Okay, and then it gives an upper bound on that speed up. However, in practice, this is usually not what happens. Okay, because when you increase your number of processors, you usually do not fix your problem size. Instead, you increase the problem size as you increase the number of processors. Okay, so for example, if let's say that we're trying to do a weather simulation. Okay, if you only have a few processors, right, then you're going to be satisfied with just a coarse-grained model for the simulation, right? You're not going to try to do a very complex simulation. Okay. However, as I give you more processors, then of course you want to make good use of those processors, and you can do that by solving a more detailed simulation. Okay. So you're going to make the simulation more complicated, so you're actually increasing the problem size, right? Because you have a more complex simulation. Okay, so in practice, instead of keeping the same problem size as you increase the number of processors, you increase the problem size as you increase the number of processors. And so Gustafson's law tries to capture this. Okay, tries to capture this phenomenon of increasing problem size. In fact, it's going to say that this larger problem, okay, we're going to call this the scaled problem. And Gustafson's law is going to say that we choose the size of the scaled problem so that the parallel running time stays the same as the sequential running time, okay, of the original problem. Okay, so let me explain this in a more clear way. Actually, let me try to motivate this a bit before I get to the equations. Okay, so I'll show you some equations to capture this precisely, but let me just motivate this a bit more. Okay, so Gustafson's law is basically assuming that as you increase the number of processors, the sequential work, the total amount of sequential work in the big problem, right, with more processors, right, versus the unscaled problem with just a single processor, right? It's going to assume that the amount of sequential work is the same. Okay, one example of this would be, let's go back to this weather prediction problem, right? So what is the sequential work for this problem, right? It could be something like initialization, okay? So maybe we need to set up some data structures or something like that, okay? But the amount of initialization doesn't really depend on how many processors you have, okay? So therefore, the amount of sequential work is the same for both the unscaled problem using one processor and the scaled problem using many processors. Okay. Now, in practice, you can look at the specific problem that you're, the program that you're actually executing, and you can look at whether this assumption is reasonable or not. Okay. You can look at whether your sequential work is the same in your scaled or unscaled problems. Okay. If it actually is the same, then you should apply Gustafson's law. Okay. But if you have a problem where the amount of sequential work actually changes as you increase the problem size, then Gustafson's law is not a good fit. Okay. Now Gustafson's law assumes the sequential work stays the same, but of course the parallel work is going to increase as you increase the number of processors. Okay, so for the weather simulation, the parallel work would be the actual simulation itself. Okay, and so that's, of course, you're going to do a larger simulation as you have more processors, so the parallel work will actually increase. Okay, so now let's actually get to Gustafson's law. So what it's saying is that suppose you have P processors. Okay, now the amount of, let's see. Okay, so let's do it this way. Okay, so when you had one processor, right, the amount of sequential work is going to be the sequential fraction times the sequential running time. So the sequential work is going to be F times T1. Okay. Now, given P processors, we want to choose the amount of parallel work so that the parallel running time, okay, is equal to the sequential running time. So how do we do that? Well, suppose we choose the amount of parallel work to be this expression, okay? The number of processors times 1 minus F times T1. Okay. Then what is the parallel running time going to be? Well, it's going to be the sequential running time plus the amount of parallel work divided by the number of parallel processors, P. Okay, so if you simplify this expression, you simply get that this is equal to T1. So this is saying that the parallel running time on the larger problem, right, equals the sequential running time for the original problem, okay, which is the assumption that Gustafson's law assumes. Okay, so now once we know how much parallel work we have to do, right, now we can look at the speed up that we're getting. Okay, because the size of the scaled problem, right, is going to be the sequential part plus the amount of parallel work, right? The amount of parallel work, again, is this much. Okay, now, if you try to solve the scaled problem on a sequential processor, okay, how much time is it going to take? Well, it just takes exactly, the sum of these two quantities, because this is the size of your scaled problem. And if you only have one processor, then your running time is exactly equal to your problem size. Okay, so for the scaled problem, right, the sequential running time, which we denote by T prime of 1, is going to be this expression over here. And now what about the speed up that we're getting? Okay, the speed up is basically comparing the sequential running time, this T prime of 1, right, to the parallel running time. Right. Well, we know the parallel running time is TP over here. This is equal to T1. Okay, and the sequential running time is equal to this expression, which is also something in terms of T1. Okay, so now you do the math, right, and then you cancel everything, and you get that this scaled speed up for Gustafson's law is going to be equal to P minus 1 times F. Okay. So now, if you want to take a more pictorial look at this, then what's happening is that So here in the scaled problem, if you look at the running time on a parallel processor, you have the sequential portion, and then the parallel portion is going to take this amount of time to run. Okay, whereas on a sequential processor, right, the running time is going to be the sequential portion plus p times this part over here. Okay, because you only have one processor, whereas here you have p processors. Okay, and the scaled speedup ratio is basically comparing the length of this sequential running time, the t prime sub 1, right, with this t of p, t sub p. Okay, so now let's compare Gustafson's law and Amdahl's law. Okay, so usually Gustafson's law is going to predict much higher speedups than Amdahl's law. So let's do some examples. So suppose you have a program which is 5% sequential, okay? And let's say that you have 50 processors. So then Amdahl's law is going to say that your speedup is going to be 1 divided by your sequential fraction plus your parallel fraction divided by your number of processors. Okay, so this comes out to about 14x speedup. Okay, whereas Gustafson's law is going to say that this expression over here is equal to p minus p minus 1 times f. Okay, and if you plug this in, you're going to get that you have almost 48 times speedup for Gustafson's law, whereas you only have about 14 times speedup for Amdahl's law. Okay, so Amdahl's law is usually called, another term for this is called strong scaling. Okay, so this is where you fix the problem size and you increase the number of processors. Okay, so this is called strong scaling. And Gustafson's law is called weak scaling. And here is where you increase the problem size. Okay, so that the running time with the larger number of processors is the same as before. Okay, so which law should you use, right? Amdahl's law or Gustafson's law? Okay, so sometimes you shouldn't use either law, okay, because both of these laws make these assumptions, right? Amdahl's law assumes that you have this the sequential portion which is completely unparallelizable, and then you have this other portion which is perfectly parallelizable, right? Is that valid, right? This might not be a valid assumption. Okay, Gustafson's law assumes that you make your problem much larger, okay, and the sequential portion always stays the same, right? This could also be invalid. Okay, so which law you use depends on the situation, right? If you're closer to Amdahl's law's assumptions, then Amdahl's law is going to give a pretty good prediction, but sometimes you might need to go with Gustafson's law, and sometimes if you have a problem which neither assumption captures, right, you have to go with something else. Okay, so now let's look at some additional ways of measuring performance, which can capture properties that neither Amdahl's law nor Gustafson's law captures. Now, one problem with Amdahl's and Gustafson's laws is that neither of them capture this issue of overhead. Okay, so overhead is different from the sequential part of the execution, right? So overhead is this increasing cost that you have to pay as you increase parallelism. Okay, so this comes from things like communication or synchronization, right? It's different from the sequential portion, right? And Amdahl's law and Gustafson's laws do not say anything about the overhead. Okay, so in order to capture the effects of overhead, then we can consider something called the Karp-Flack metric. Okay, so this is intended to capture the overhead, and it does it using empirical observations about the running time of the algorithm. Okay, so the way this works is that given a program, right, so let's let T1 be the running time of the program using one processor. Okay, now this includes, so this T1 time includes two parts. It includes TR, which is the parallelizable part. Okay, and it includes this part TQ, which is both the sequential portion of the program plus the overhead that we need to pay for parallelizing. Okay, so now we want to look at this sort of serial fraction, which is defined as this TQ, which is like this extra cost that you have to pay, right? It's the non-parallelizable part of the computation, right? We want to look at TQ divided by the overall running time. We're going to call this E. Okay. Now we don't really know what E is. Okay. So in Amdahl's law, we assumed that we could somehow we knew how much of the program was actually sequential. Okay, but here for the cart-flat metric, we don't assume that we know E. Rather, we assume that you can do some experiments, right? You can actually run the program, and then you can use those running times to determine E. Okay, so let's do some equations over here. So if we set TP to be the running time using P processors, okay, then this is going to be equal to, well, again, we have this overhead plus sequential part over here, right? This TQ, okay? And then for the parallelizable part, this is going to be TR, right? So that's how much is parallelizable divided by P, which is the number of processors we're using, okay? And so this is going to be equal to, so TQ is equal to T1 times E, right? Because E is defined as TQ divided by T1. Okay, and then this other part is whatever is not part of the overhead or sequential part, right? That part is going to be belong to TR, right? So this is T1 times 1 minus E divided by P. Okay, so now if you look at the speed up that you get, right? Speed up is going to be TP divided by T1. Okay, well, this is actually 1 divided by the speed up. Okay, so this comes out to be equal to this expression, E plus 1 minus E divided by P. And this is equal to 1 divided by your speed up. Okay, now you do some more simplification and you get that this E, right, the sequential part plus the overhead is equal to this expression over here. Okay, now this expression, let's look at these terms. Okay, so we have this SP term. Right? This is the actual speed up that you're getting with P processors. And you can determine this just by running your program with P processors. Okay, and then of course you know P, right? So using both of these quantities, you can compute E. Okay, so now let's do that. Okay, so we have this expression for E over here. And suppose you have a program where if you run this program, and vary the number of processors, right? You're gonna use 2, 3, or more processors, right? And then you measure the speed up as you use these different numbers of processors. Okay, then you can just plug in this SP value into this E expression to get the value for E. Okay, so if you do that, you're going to see that the E values are going to be something like 0.07, 0.075, and so on. Okay, so in this example, the E values are actually increasing. Okay, now remember that these E values include both the sequential portion and the overhead. So the fact that this is increasing is saying that the overhead for the program is increasing as you increase the number of processors. Okay, so you're paying more and more overhead as you increase the number of processors. Now, if you go with a different example, right? So again, here we increase the number of processors from 2 to 8, right? And suppose that now we measure a different set of speedups. Okay, suppose you measure speedups of 1.82, 2.5, and so on, right? Again, you can plug these SP values into the E expression, and then you're going to compute these E values, right? And then all of these values here are equal to 0.1. Okay, so then this indicates that for this program, right, the overhead you're paying, which is included in this E value, right, this is not increasing as you increase the number of processors. Okay, so therefore this program down here, right, this is somehow a more scalable program than the first program because you don't pay increasing overhead as you increase your number of processors. Right. So eventually, if the overhead for the first program keeps increasing, we're going to get less and less speed up as you increase the number of processors, right? Whereas here, right, you can basically, because the overhead is the same, right, you can get better speed up as you increase processor count. Okay. Now, one problem with this cart-flat metric is that you notice here that we're only varying one quantity. We're varying the number of processors. Okay, but there's another quantity that you can vary for a parallel program, which is the size of the problem. Okay, so and when we do that, we can actually capture more accurate information about the problem, about the speed up. Okay, so next we're going to look at a way to measure the efficiency of a program by both varying the number of processors and the problem size. Okay, so to do that, before we do that, I just want to remind you about these about this notation that we have for computing asymptotic efficiency. Okay, so remember that asymptotic efficiency basically means that we want to compare the sizes of two functions. Okay, and you want to do that as the size of the argument increases, right? So we have these 5 operators, or five ways of comparing, right? So you say that the function f is big O of g, and this basically means that f is not bigger than g. Okay, so the formal definition would be that as you make n very large, right, then this this quotient over here is bounded. Okay, we also have that f can be big omega of g, and this basically means that f is at least as large as g. Okay, and then we have these other expressions over here. F is theta of g means that f is equal to g, right? Intuitively means that f is equal to g, and then little o means that f is strictly less than g, and then little omega means that f is strictly larger than g. Okay, so this is our notation for comparing the sizes of two functions. Okay, so now we're going to look at this measure called isoefficiency. Okay, so this is a way to sort of balance the overhead that we have from parallelizing. Okay, so for isoefficiency, we're trying to maintain the same efficiency for a program as we increase the number of processors. And the way we can maintain the same efficiency is that we can increase the problem size. Okay, so unlike the Karp-Flack metric, here we both increase the problem size, the number of processors and the problem size. Okay, so so the way we're going to do this is that suppose you have a problem of size n. Okay, so this is the problem size, and suppose you're using p processors. Okay, so now let's let w of n be the amount of useful work that's being done by the processors. Okay, so this is all the work that does not include the overhead. Right, so the total amount of work done by the program includes both the useful work and the overhead that you're paying from parallelizing. Okay, so Wn is just the useful work that we're doing. And then this gamma thing, gamma is the amount of overhead that we're paying from parallelizing. And this gamma is a function of both the problem size and the number of processors. Okay, so yeah. And so both W and gamma are going to increase as you increase the problem size and the number of processors. And now the efficiency basically measures the amount of useful work that we do divided by the total amount of work you do. Okay, so the total work is the useful work plus the overhead. Right, so if you simplify this, this is going to be 1 divided by 1 plus the overhead divided by the useful work. Now for isoefficiency, our goal is to maintain the same efficiency as we increase the number of processors. Okay, and how can we do this? Well, this overhead here is increasing as you increase the number of processors, but if we can increase W also, okay, then perhaps we can keep this fraction here the same, right? We can keep gamma divided by W the same, okay, as you increase P. If you increase W at the same time, then maybe you can keep this fraction here the same, and if that happens, then we can maintain the same efficiency. Okay, so what we need to look at is the relative rate of increase of W versus gamma. Okay, so let's first look at this qualitatively, and then we'll give some actual numerical examples. Okay, so now first of all, suppose you have a problem and you increase the number of processors, but you keep the problem size the same. Okay, then usually the overhead that you pay is going to increase faster than the work that you're doing. Okay, because in fact the work you're doing is going to stay the same if n stays constant. Okay, but as you increase the number of processors, you're going to increase the overhead. Okay, because, for example, you might have to do more communication or synchronization between the processors. Okay, and because we know that the efficiency, right, is equal to 1 divided by 1 plus the overhead, right, which is a function of both problem size and number of processors, right, divided by the useful work that we're doing, right, then so if this increases, right, but this stays the same, right, then our efficiency is going to decrease. Okay, so this is what's being shown on the left over here, right? This is for a fixed problem size, a fixed W, right? As you increase the number of processors, your efficiency decreases because your overhead increases. Okay, now on the other hand, we can increase the problem size, but we can keep the same number of processors. Okay, in that case, the amount of useful work is going to increase, and the overhead might also increase, but usually W increases faster than gamma. Okay, and if W increases faster than gamma, right, then you see that this fraction over here, right, is actually going to this fraction is going to decrease, and so your efficiency is actually going to increase. Okay, so this is what's being shown on the right over here. So here you fix the number of processors, but you increase W, and this is going to improve your efficiency. Now for ISO efficiency, what we want to do is to both increase the number of processors and increase W, but to do this in a way that they balance each other so that we can maintain the same efficiency. Okay, so we don't want our efficiency to decrease, and we also don't need it to increase. Okay, so by increasing both P and W at the same time, we can maintain the same efficiency. Okay, so that's what ISO efficiency is. So now let's do some actual examples for this. Suppose we have a problem where the amount of work as a function of problem size is equal to n times log n. Okay, and the overhead is going to be n times log p. Okay, so this is our assumption for the problem. Then what we see is that the efficiency is going to be equal to 1 over 1 plus the overhead divided by the work, right? So if you simplify that, you get this expression, right? So now we want this to be a constant, okay, for ISO efficiency. And so that means that we want this to be some sort of constant, okay? So in order for this thing to be a constant, right, then we need log n to increase at least as fast as log p. Right, you need the denominator to be at least as large as the increase at least as quickly as the numerator. Okay, so as you increase p, right, you also need to increase n. Okay, so how do we do this? Well, if log n is omega of log p, then that just means that n is omega of p. Okay, so as long as we increase n at the same rate as we increase the number of processors, then we can maintain ISO efficiency. Okay, let's do another example. Now here, suppose that the amount of work is just n, right? And suppose the overhead is going to be this expression, okay, this complicated expression. Now here, if you want to have ISO efficiency, then again, you need a W, right? You need W of n to be omega of this overhead term, okay? And since we have two parts for this overhead term, we're just going to do this separately. So we need W of n to be omega of the first term, okay, omega of p to the 3/2. Okay, and then we also need W of n, which is equal to n, right? We need this to be omega of the second term. Okay, so now here you need to simplify things a bit, right? So you get that n to the 1/4 is equal to p to the 3/4, and so this implies that n needs to be omega of p cubed. Okay, and the first term only needs n to be omega of p to the 3/2, so this term here is going to dominate, right? So we see that as long as you have n is omega of p to the 3rd power, then you can maintain the same efficiency. Okay, so one final example here. So suppose you have omega, the amount of work is n squared, right? And the amount of overhead is going to be n squared times log p. Okay, so now if you look at the isoefficiency expression, right? Or sorry, the efficiency expression, you get that the efficiency is equal to 1 divided by 1 plus the work divided by the overhead, and that's going to be log P. Okay, so you see that here, as you increase P, the efficiency is always going to decrease. Okay, no matter how you increase the problem size, you can't keep up with the rate of increase of the overhead, right? And that's basically because the overhead here is equal to n squared log P, whereas the work is just equal to n squared. Okay, so the overhead is always larger than the work. Okay, so therefore, as you increase P, your efficiency is always going to decrease. Okay, so in general, whether you can maintain isoefficiency depends on the sizes of these two functions. Okay, so that's the end of this lecture. And next time, we're going to look at a programming language for parallel computing called MPI. Okay, so talk to you next time.